Tangent planes of explicitly given functions. We've already discussed how to get the tangent plane when a surface is given implicitly. Well, what if you now have the graph of a function, okay, and it's given explicitly? What do we mean by explicitly? That the dependence of f on xy is shown clearly. You know, you get x squared plus y squared minus 3 or something, right? So you have that explicit dependence shown, and you get a graph. Now, we've already dealt with implicitly defined surfaces and gotten the tangent plane for them. And we could use that same machinery again for explicitly defined functions. Once you notice that if you have a graph, you could describe the graph of any function implicitly by using this type of relation there. So you just define a new function, capital F of x, y, z. Now this is a function of 3 variables. Set it equal to z minus fxy, the explicit dependence on x and y. Set that equal to 0, and you have the graph of the function as implicit surface there. Okay. Now, with this in mind, we just plug it back into the machinery that we had before. You take the gradient of the function of 3 variables, and you'll be left with this at the end. Okay, so what's important about the gradient of the function of 3 variables? Well, it's going to give you a normal vector to the level surface, right, for the implicitly given surface. So we have our normal vector, and our point is going to be the point AB, and the z is going to be FAB. Okay, and just like that, you are now given a way to get the tangent plane for explicitly defined function. So we here's our normal vector. Here's our vectors that are running along the plane. They should be orthogonal, and we have this from the computation we carried out above. And dotting and simplifying, we end up getting this relation here. Now the z, you could have just left it over here, the z on the left hand side, and had the 0 there, or you could simplify and write it this way, either one. What you're seeing here is the tangent plane for an explicitly defined function. And one of the reasons why I wrote z here on one side of the equation is because you can now look at this right hand side as a sort of linear approximation. Okay, if a tangent line is the linear approximation for a function of one variable, then the tangent plane is the linear approximation for a function of 2 variables. So this z could be considered a function of 2 variables. Right? This z for the tangent plane could be a function of 2 variables, lxy, which we call the linear approximation, and this right hand side is the exact same as the right hand side here. Okay, so if you can approximate a function by the tangent plane in this way, and this linear approximation idea even extends to functions of 3 variables and higher. So you use a similar formula that you have above, except now you have this extra f sub z to get the linear approximation. And of course, this isn't quite a plane. You get the plane when you have functions of 2 variables. Functions of 3 variables, visualizing that is a little less clear. Nevertheless, this is the linear approximation for a function of 3 variables. So let's take a concrete example. So we have the function given explicitly here. Fxy is equal to 32 minus 3x squared minus 4y squared. That is an explicit representation of that function. And, well, we want the tangent plane at the point 2, 1, okay? Which, if you include the the z value there, 16, it would be 2, 1, 16 on that surface, the graph of that function. Okay, and we just basically use the formula that we have above. Here's the linear approximation, which is again, the same as the tangent plane if you just write z instead of l there. And you have, you need to compute the partial derivative with respect to x. That's minus 6x, partial derivative with respect to y. And we want this tangent plane at the point 2, 1, so we evaluate these at the point 2, 1. We get minus 12 and minus 8. And we also need this FAB, which here is F21, since we're evaluating it to 1, and we find that it's 16 there. Then we just use that formula that we have above. Okay, z is equal to what you see here, and using that formula that we have above, we have this equation here, which plugging values in, so 16 for this, for example, Fy21 is minus 8, which we found here, and simplifying, and we have that z is equal to this. This is the tangent plane, so if one is asked for the tangent plane, it's the boxed in term that you see over there. Now, what if one is asked for the linear approximation? Okay, so you know, it's written here tangent plane and well, linear approximation is the same thing, except that you just use LXY instead of Z. Okay, it's you know, we're getting a function of two variables which we'll call LXY. So, but they're equal to the same thing, right? You know, this tangent plane you could write more generally. You could even move the Z to the other side. So, but the function of two variables that you would get for Z is the linear approximation. And the final word is about changes along Z of the tangent plane. So we could look at changes along Z from the linear approximation to the point FAB on the graph. Okay, so we could look at that difference. And just looking at this formula and moving this to the other side, we end up with this term here. We can identify dx with x minus a, dy with y minus b, and dz with l minus fab. And what this helps you see is changes along z that occur due to dx and dy. Now those changes are approximations, right? Since we're using the linear approximation of the function, but nevertheless we are able to compute changes using this formula. So what you see here is the in orange there is the graph of the function that we looked at when we computed the tangent plane of an explicitly defined function. So here you have the graph 32 minus 3x squared minus 4y squared, and we computed the tangent plane, and it is right here at the point 2, 1, 16. So that equation for the tangent plane is the equation of that plane there.